So we'll proceed with the next keynote, the last keynote of our conference. We have Professor Saroj Kumar from ISI Bangalore. So I request Dr. Sujit Das sir to introduce Professor Saroj Kumar.
Very good morning to respected resource persons, respected professors, and dear participants and my dear students. So today we are very much fortunate enough to have with us Professor Saroj Kumar. Sir will be delivering his thought on domain adoption approaches for efficient pattern classification tasks. Now it's our moral responsibility towards our participants to briefly introduce our respected speaker today. Saroj Kumar is an associate professor of the System Science and Informatics units at ISI Bangalore Center. He received BSc degree in Physics Honours from Sambalpur University in 1990 and MSc degree in Physics with Electronics specializations and a PhD degree in Science from the National Institute of Technology, Rourkela in 1997 and 2003 respectively. He worked as a senior research scientist at research and development units of various industries in India for about 3 years. He was awarded many times for his excellent contribution to various critical projects. He worked as a postdoctoral fellow and visiting assistant professor at ISI Kolkata in 2005-06 and 2009-10. He received the most prestigious Sir J.C. Bose Memorial Award of the Institute of Electronics and Telecommunications Engineers, India in 2003, and most prestigious Odisha Young Scientist Award for research in electronic science and technology in 2003. He is a senior member of IEEE since 2011. His current research interest includes image processing and analysis, including remote sensing, pattern recognition, granular computing, domain adoption, adversarial machine learning, and many more. Sir has contributed about 80 research papers in various well-known and prestigious journals, internationally referred conferences, and edited monograph volumes. One granted US patent also goes to Sir's credit in the year 2015. Now I will request Sir to share his thoughts towards our participants.
So good afternoon, everyone. So how much time I am allowed to speak?
You are between our lunch.
So as long as you are not hungry, I am allowed to speak, right? Thank you for this generous introduction. No, so I think I'm able to best. So I'm a faculty in Indian Statistical Institute. So I belong to this. We have a Bangalore center. Our head office is in Kolkata. And thank you to the organizer, Dr. Sanjay, for giving me the opportunity to have a face-to-face discussion with you all eminent people. Thank you for that. So the today's point of view is domain adaptation approaches for efficient pattern recognition. It's a general aspects, a general theme. So it can be applicable to anywhere. So there is nothing like in this particular application or that application this will be applicable. It is applicable to any efficient technique process. Whatever just now sir was telling. So you do all this pre-processing. He did all this pre-processing. So once the data comes to me, I'll just give the decisions. Right. So there is a machine learning component is there at the end of these things. I think you might have seen that one. So before going to that one, I'll pre-assume something. Okay, I expect that you all know that one. I don't need to explain all these things. So I'll just directly go to that particular aspects of this today's discussion. So I assume that these are all everyone knows that one. Whoever is talking about the decision-making process and everything. So everything known to you. So I assume these followings are known to you. So I will not spend on time on these things. And they are you all know what is a decision is all about, right? And that decision I am expecting a machine should take. That's what the pattern recognition is all about. And this is how a pattern recognition system looks like. Okay. So here your input goes and your output comes. Fine. So let's skip these things. Now coming back to the actual point of discussion, the domain adaptations. Now before going to that one, let us briefly try to understand what is machine learning and what are the challenges. And you all know what machine learning can do. It can do anything. Okay. So yesterday I was talking with my colleagues. So it's like a potato. I was using potato, aloo, something like that. The way you utilize it, you'll get its own taste, right? Right? You understand that, no? And if I got the potato in circle form, I'll fry, I'll have a different taste. If I make it in a square size, rectangle size, whatever be it. But the main purpose of telling all these things is that it is something ingredient is there. You utilize whatever the way you like it to be tested. Okay. So that is what the machine learning is all about. And it can do anything. Because at the end of the day, you have to take a decision and you have to use the machine learning. Fine. And this machine learning quite successful with deep learning methodologies with the more and more amount of data. Right? So it has some assumptions. Assumptions, under certain conditions it works. It doesn't work otherwise. What are assumptions? Assumptions are like this: machine learning or deep learning. ML belongs to machine learning, deep learning. Okay, come. Availability of large amount of level data. Expertise. Availability of expertise is required to work under the machine learning environment or deep learning environment. Whatever techniques you talk about. So we want expertise. You know what is the purpose of the expertise? Because we need to train that model. Okay. So machine learning and deep learning assumes that there is a large amount of available expertise. Second thing, training and testing domains are same. These are the assumptions, general assumptions. Okay. Those who are working in these machine learning areas, I think they are doing all these things. Training and testing domains are same. What does it mean? From a domain, we take some data, and what we do? We take some portion of the training, some portion of the testing, and we build a model on training and testing. That means our data are coming from the same data domain, right? That is what the meaning of test and training domains are same. Feature space of the both domains are same. Whatever features I am using for during the training, same features I use for testing. Don't you agree with me? This is what the machine learning does, right? Data distributions of the same. Distributions of the data. Where from that data is coming? What is the distributions? Distribution, statistical distribution I'm talking about. Okay. Availability of lots of time. Machine learning assumes that we have lot of time. Do we have time? Do we have time? Time is money, right? Now money has no value. Time has value. I used to say, if I have taken 10 rupees from you, there is a possibility that I can return you back. But if I have given 1 second from my time period, can you give it me back? Whatever the way you like. Can you? So this is how money is time, right? But machine learning and deep learning assumes that we have a lot of time. Why? In what aspects I am telling? Because your data changes, model changes. Domain changes, but model changes. Your statistical distribution changes, model changes. Your frequencies, spaces are changes, feature space are changes, model changes. That means for each and every problem, there is a model. Can you apply a model which is used for a particular problem in a different problem? Not possible. Okay. So that is what we human beings are, I mean, expertise in. We can deal with many problems. That is the beauty about the human brain, human machines. Okay. So in that concept, I'm telling, we have a lot of time. That means for every problem, we can build a model. And different features means it's a different model from different scratch. Different domain, different data, different collections. If I collect the data, model is different. If you collect the data, the model is different. So we have a lot of time. That is why the assumptions of machine learning and deep learning. Okay. These assumptions are actually the challenges of machine learning. Don't you think that? These assumptions require to work in machine learning model. But you just try to understand, these assumptions are actually challenges for machine learning. Assumption becomes the challenges. Do you think that we have a lot of expertise? We have limited expertise. Even in some cases, we don't have expertise also. We talk about unsupervised way of training and building the models. Okay. So we don't have expertise enough. Training and testing domains are same. This is the assumption of machine learning. But in real-time scenario, may not happen. I have learned from one domain, but I will be tested in a different domain. Does it not happen? Let us say very simple examples I'm talking about. In IT industries, who is eligible to enter to IT industry? Is there any specific answer to that? I mean, in terms of technical background, if I'm talking about, who is eligible to enter to an IT domain? IT domain, you all understand, right? Who is eligible? We assume any specific answer for that? Is it a computer science background can enter? Is it an electrical person can enter? Is it an electronics background can enter? So, what is the answer actually? Is it necessary that a person should have a BTech in or computer science background to enter to the IT department? Do you agree with me? No, not necessary. But are they not doing well? Are they not being paid? Are they not competent enough to the computer science department? How is it happening? A civil engineering or a chemical engineering or a metal engineering background is trained in a different way, but working in a different way, but still competing with that computer science person. How it is happening? So in that cases, don't you think that training and testing domains are different? They're different. Feature space of the both domains are same. I have taken 5 features during the training. If I increase the number of features during the testing, does it work? Your machine learning model? It will not work. Or in a different features, if I have taken, does it work? It will not work. So that is a challenge for machine learning. Distributions of the both data are not same. Same thing. Availability of a lot of times. We don't have time. Who has time? Nobody has time. And machine learning assumes that we have a lot of time. But for everything, we are building a new model. Okay. So these become the challenges for machine learning and deep learning. Okay. And how to deal with that one? It's not a big problem. We are all thinking that machine learning can do whatever the way it likes. Whatever the way you like, we can utilize that. But these are the big challenges. In real-time scenario, these are the basic challenges what a machine learning and deep learning is to work properly. Okay. But the big challenges in supervised model or something can be compromised or can be adjusted or can be compromised with some extent, like limited sample data are there, but lot or level data are there. So to some extent, we can adjust that one. Okay. But in a great way, it fails. The model doesn't work. One possible solution is you create your level data. If somebody is telling, I don't have level data, you create data. If I know the statistical distributions of the data with the same statistical parameters, I can generate the data set, a synthetic data. But do you think that they are same? No, they are different. Whatever I'm seeing with my eyes, is it same thing as somebody has taken photograph of the same thing? There is a difference. Okay. So these are the kind of problems we face in decision taking process. How to deal with these? Although large level data are field level, but this is not really but bias is researcher. That means our model is biased towards the way we are learned. Okay. So your problem will never be exactly same, and standard data set will never be worked out. Fine. Other possible solutions is something like that. So these are the motivations of the another seat or another paradigm, we can say, another way of taking these years. Okay. So when machine learning and deep learning assumes these things, and we don't have that assumptions really available, so we need to go for alternative solutions. So this is what the alternative we call it as a domain adaptation. Traditional machine learning assumes, so these are the motivations for domain adaptations. For everything there is a motivation, for everything there is a reason, right? Okay. So what is the reason for you people are sitting here? Because you are listening. What is the reason for I am standing here? I am speaking. So there is a reason for everything. Okay. So motivation for domain adaptation is something like this. Traditional machine learning, this data space, same distributions doesn't work in real-time scenarios. In real-time scenarios, the dynamics are very peculiar. Okay. We don't get the same training samples. We don't have the same testing samples. We don't have different domain samples. And so many problems or issues are there. Insufficient level data sets in poor prediction performance. When expertise is not there, obviously your performance will be affected. Okay. Lots of unrelated existing data from different sources. Is it necessary that while training, I will learn from a particular source of information? Not necessary. It's a simple example. When a baby is there at our home, do you think that that baby learns only from the parent? No, not necessary. The baby can learn from different sources of information. Now, how that variations, the way I speak will be different from somebody else speaks. The way I teach, so one more teacher is there teaching. So our way of giving training is different. Now, how that person actually takes the benefits of all these different sources of information. So that you are the motivations. Okay. Start from scratch is always time consuming, correct? I have a model. I have a new problem tomorrow it came. If I start doing all this from the beginning, then it's a big problem. That means whatever expertise I have already, I'm underutilizing those things. I'm starting that learning process again once more. Okay. And that solution may transfer knowledge from other sources may help. Okay. Some challenges, some pictorial form I can say. What do you see? Challenges of machine learning and adaptation for dumb learning. See, these are some of the photographs, and these are some of the photographs. Now I built a model on these photographs, and I will apply those models on these photographs. Will it work? You see, they are different actually. I will try to understand it. They are different. The scenarios are different. The domains are different. The purpose of doing all these things are different, completely different. So training domain and testing domains are different. How I can build a model on these training samples and test on these samples. So that is why the machine learning are always biased to the data sets. It is always biased to the feature space and distributions. You all know that. Okay. Challenges of machine learning and motivations for domains and other things. If you train these things here and apply all these things here, probably it may work because you can see there is a similarity in the domains. But if you train the model on these data sets and test on these data sets, will it work? See, this is the problem comes. On the road, you will find some car and trees and all these things. Because your model knows that some behavior, whatever it is seen here, is similar to the behavior, whatever you see here. So the problem comes here. Now, if I apply that model on a tunnel kind of thing, the model doesn't understand that data is taken from a tunnel. Okay. So the domain is different, scenario is different. Okay. The features, informations are different. How can we make use of that expertise, whatever we already have, for the present situation? That is what we call domain adaptation. Something like this. A data is collected from here, model is built here, but tested on these things. Model is built here, tested on these things. Model is built here, tested on these things. Some CAD model, but real. So they are different domains. How to deal with those things? And that is what the meaning of domain adaptations. So I'm going very quickly. Okay, so if any confusion is there in your understanding, just let me know. So what is domain adaptations in a pictorial form? If I want to discuss, this is one domain informations, and this is another domain information. You see, characteristics are different. Now, what I'll do in normal conventional machine learning, we build a model using these data sets, and a similar data set will come here, and I apply this thing on here. Okay, so this is what normal machine learning does. Similarly, for this data set, I will build a different model, which is different from model A and model B, and I apply here. That means for two different data sets which look similar geometrically or in any way, some format, I have to build two different models, and I have to spend a lot of time on these things. Can I not do something like this? I build a model here. When I am going to utilize this one as a test domain, I use my previous expertise and do something there so that this model should not be start from scratch. Okay. So from some level, it start learning. That means I'm trying to learn this domain from here. So learning a domain adaptation. I'm adapting this domain from here. Similar simple example, just now I was giving that IT industries people. Anyone can enter to the IT industry side. A computer science engineer, a electrical engineer, a electronics engineer, a civil engineer, mechanic engineer, simple science graduate. Anyone can. Then what is the difference between that? Even computer science engineer enters to that one, probably it doesn't require much training. Whereas the other range people when enters to the IT, they may require some 6 months or 1 year's training. Now tell me, if after 6 months, if I want me to compare these two people, one has come from computer science department, another has come from, let us say, mechanical department. And after 6 months, if I want to evaluate these two things, I realize that both are performing similar. Now, what is your understanding here? Who is better than whom? Are you getting my point? A computer science students and then mechanical students, they are evaluated after 6 or 1 year. Now, what is your opinion? Among these electrical and computer science and mechanical, who is better than whom?
Both of them are trained for 6 months.
Oh, yeah, both of them are trained.
Long branch is better. Long branch people are better.
Right? You're understanding, right? So the ability to adapt the systems for the mechanical students is better than computer science students. So this is what the human expertise or human way of taking decisions. We just want to put that aspects in machine learning, and we want to improve the performances. Okay. So this is what we all about the domain adaptation. So in classical scenarios, what happens? Training domain, model, test domain, and we got these things. The moment we change this domain here domain X and here domain Y. So you see there is a drop down in the performances. This is obvious. We all have realized this. Now, how to deal with this one? This is what the domain adaptation is all about. TL, transfer learning. That means my learning is getting transferred from one domain to other domain. My adaptation is happening from present domain to another domain. Okay. So that means whatever I have learned till today, that I am going to utilize in future. That I am not throwing. Do we throw? Whatever we have learned today, do we throw our past experience? No. We utilize that expertise to adapt the present scenarios, to adapt the present problems. Okay. So this is what the domain adaptation is. So we say there are two terms you can see here: source domain and target domain. Source domain is from where you have learned from the beginning, and target domain is the domain where we are applied, you are evaluated. Okay. So we build a model here from source domain, get the knowledge, and with that knowledge, do something and build another model which can be applied to the test domain. So it's good, no? I'm not losing the previous expertise. With minimum effort, I can get a better accuracy than this one. Okay. So this is what it is. Basically, when distributions of the data and target domains is different from source domain, then we require that. And that is what in real-time scenarios we all are having. Okay. Domain adaptation aims at learning from the source distribution and performing the different target data distributions. Right? So dividing models that can cope with this shift is approach called domain adaptation. So we call it a shifting of informations. Okay. So we use a term called shift. Domain shifting. Start from where you have started and from where you are applying your expertise. Okay. So there is a shift of informations. So if that I can compute that shifting, in what rate, in what way that shifting happens, then probably I can utilize my previous experiences and perform well in my present scenarios. Okay. So it has also been seen beneficial for learning unrelated sources. You got my point? When more than one source is available to one problem, that means there are certain scenarios. I'm trained from one domain, but I will be tested on n number of domains, which are different from the trained domain. You try to understand that one. See, this is all about two different domains. Now, when I'm telling that two different domains, actually they are not exactly disjoint domains. They are not completely disjoint domains. We can say they are all related domains. Okay, they have some level of overlapping of informations. Otherwise, it's impossible. Practically, it is impossible because if I'm tested in one domain which has no relations with the target domain, probably I may not utilize my previous expertise. Okay. So when more than one source of distribution is available, problem is called multi-source domain adaptations. Right? So on practical examples, I am telling. This is one class and this is another class. So in machine learning and deep learning, what we do? We put a boundary. That is what the classification is all about. Right? So this is class 1, this is class 2. Now, if I want to test this model on this data set, will it work? We will try to see the shape size. At least one particular features I can say shape of the objects. Here plot sign, minus sign, and here circle. I train my model on this two data set. Class belongs to class 1, this belongs to class 2. But I'm testing that model on this, which is completely different. Color is different, shape is different. Does it work? Normally, machine learning doesn't work better in the way. It will work. I mean, see, when I'm given a question, if you are asking something, I have to, the moment I have to tell something, I may commit a mistake also, correct? Right? So machine learning is something like that. If you allow or ask a question to a model will give you some answers. So here, machine learning, you will have some output, but it will not be the best one. You may not like that one. Okay. So probably it will have like this. Okay. So in that kind of scenarios, we need to develop or we need to do something here during the decision taking process so that it will adopt this domain information to this domain and perform a fair decisions on this new domain data. Okay. So this is what happens in details, little bit technical side if you want to go. So this is the source domain, level data, all these things are there. This is target domain. See, try to understand these two domains are not same. That's why it is called source domain and target domain. They are not completely different, but relatively different domains. Okay. So some kind of domain development algorithm here it is done. So what do we? I mean, what is the algorithm says is that we do some level of computation, some level of manipulation, some level of characterization here during the training stage, so that will work on the test domain. That is what the purpose is. And in a broad visualizations, you can see it is a part of this called transfer learning. Okay, learning is getting transferred from one domain to other domain. Okay, so the domain adaptation is one component of this transfer learning. This is the broader visualizations of the transfer learning methods. So there are different ways of doing there. So it starts from here. There are different branches, and your domain adaptation is a portion of that one. Okay, so this is the broader visualizations of that one. Definition wise and setting wise, we can have domain adaptation in different way. Supervised, unsupervised, semi-supervised, one shot, zero shot. These are the different learning methodologies. How you are going to adapt your current domain to the future domain. Okay. Supervised means both the levels are same. That means I have level data or expertise from the source domain. I have level data from the test domain, and I will just do some kind of mixing or computations, and there I will design the model. Unsupervised means large source domain and no target domain. I don't have any information about the target domain, but I have information about the source domain. Source domain means you are understanding from where the model started learning. Semi-supervised means, I mean, these are the conventional terminology in machine learning. Those things are getting transferred to domain adaptation. I mean, in that particular area. So we are trying to utilize that techniques of machine learning, but we are going to do some kind of manipulations. You can say processing. You can say some kind of computations. You can say. So there are some terminologies that let us not discuss more about all these things. So little bit mathematics. Let me not go inside that one. So one basic way how to deal with this domain adaptation kind of thing. So what they do is that you see, you can easily see everything is explainable here. So they do some kind of overlapping. Overlapping in the sense they do some kind of alignment in the features influences. Because you know what is the meaning of features? Features are nothing but the informations on which you build a model. So that information plays a very crucial role in the performance of your model. If that information is not accurate, not fair, not good enough, probably whatever you do, your model may not work properly. No, if I catch that particular component of that whole machine learning process, from the training to testing, from the source to target, probably I can do something on that one, and which will help me to build a domain adaptation model. So in a generic 6, as I told you, so what people do is that they take some source domain data, they build some kind of model here. No, here machine learning model. I just taken it from here, so there is nothing my contribution here. So one model is here, so which extracts informations, you know, feature extraction using different kind of feature extraction methodology. So here they have used some convolutional neural network which extracts some informations. So they pre-train that model on the source domain and they extract some features, and the pre-trained model they apply on these things, because extraction of features doesn't require the level. You just extract the information, whatever they do. After extracting information from here and here, they do some kind of matching, they do some kind of alignment, and that is where the whole theme is. I mean, that is the core of this whole domain adaptation thing. Okay, how you are going to match those two information. Information is collected from source domain, information collected from the target domain, and you are doing something here. This is the crucial role where domain adaptation models are being built. So this is what the idea is: align features distributions. So feature space from here, feature space from here, and those things are getting aligned, and those aligned informations will be fine-tuned here with these convolution things, and then the rest of the things you do. Okay, this is the normal model development you do. Okay. Yeah, in a specific, I mean, I'm having an image here. Let us say CNN model you have taken. You train that model. Train models extract the information, and the same thing you extract from the test domain, and these two things you got. Now there is a short space alignment. This is the FS. FS in features from the source domain. FT is the from the target domain. These two things are aligned. Okay, how to do alignment? There are several methods out there. Let me not talk all these things on these things. So you do some kind of processing here, and those features you pass on to the, you know, the deep learning models. At the end, you put some kind of classifiers where you put your features and get the decisions. Okay. So you do that one, and this is what the. So in a very, I mean, broad way, if we want to understand what, how, and when, what is that one? It is nothing but transfer of knowledge. How to transfer that knowledge? That is what the domain adaptation is. How define an algorithm that extracts this knowledge and label it over it. And when? Okay. So let me just now how much time I can 5 minutes. So these are actually the general concept of domain adaptation, whatever till now I discussed about. So recently we worked on that, and I'll just show a and the case studies on that one. Okay, we applied that one on remote sensing data. You know what is the remote sensing data? Have you ever seen remote sensing data? Have you ever seen anybody has seen remote sensing data? Yes or no?
Yes.
Where?
Satellite images, like where we cannot go directly.
And others have not seen remote sensing data? Don't you use Google Map? What is that Google Map?
So the GPS.
It's a remote sensing data only. Nowadays, I don't think anyone can even survive without Google Map. The moment we come out of our house, we open our Google Map and you can just travel wherever you want. Okay. So how things are, so that is applied on that kind of thing, remote sensing data sets. Okay. And one case studies we have done. So it is something like domain adaptation with interpretable ELM. This is the model name. Let me not go to the detail of that one. Interpretable term is, you know what is the meaning of interpretable? That means explainable model. Normally what happens, I build a model, I train that model on that, train the model on training data and apply on that test data. Now I will not be in a position to explain that model how it works. It's the same thing. You have taken a decision, let us say. Now if I'm asking how you have taken the decision, can you explain me? Can you tell? You something like that. I'm asking something, you have answered me. Now if I'm asking you means I'm asking your brain, correct? Now if I'm asking your brain how you have taken the decision, can you explain me? You know how your brain works. Do you know how your brain works? No one knows. But it takes the decision. This model is interpretable model. That means this model has an explanation how it works. Now, is there any advantage? If I understand the working principle of my own brain, is there any advantage for me? Is there any advantage or not? Anyway, really is there to take a decision, why should I understand how it works? That is what we human beings do. Have we ever tried to understand how our brain works? We don't do. Why? Anyway, its job is to take the decision. This doing, why shall I scratch my head to understand that process? Okay. So actually I may face some problems if the model is not, if it is a kind of black box. We normally use a term called black box model. A model which is not explainable. We cannot explain that model. Okay. I don't know whether you can realize or not whether explainable model is good or non-explainable model is good. Okay. So try to get that answer. Okay. So always we should prefer for a explainable model, so that we can do something more on that one and we can improve the part. What the meaning of interpretable? I can interpret the working steps or working principles of that modeling process. Okay. So anyway, I'll just go to the this one. And there are a lot of things are there, so I'm not going to that one. Bit by bit techniques are there, and we developed 5 models here. You see, a conventional, ELM, extreme learning machine. It's a kind of simple neural network. Okay, it's a model. Let us not go to that. It's a simple model which is a kind of one-pass learning model. You know what is the meaning of one-pass learning model? When you learn, we are exposed to the trained sample again and again. Don't you do that? The moment you are reading something and trying to understand, do you read first time and you understand everything? No, right? We read again and again. That is what the meaning of iterative way of learning. So this ELM actually okay, this is the block diagram. You can see this is the complete story behind this work actually. So this ELM, what I was saying, it's a one-pass learning. That means your model can learn with one pass going of your information. It doesn't require a iterative process of learning. In one shot, you can learn that one. How beautiful is it? In one shot, I can learn everything, whatever I'm going to learn. That is what the meaning of ELM. Okay. So that is the advantage of ELM over simple neural network. Okay. So interpretable rule-based fuzzy ELM, complicated term acronyms is there. So this model we develop with an interpretable architecture. That means I can tell how it works and under what conditions it doesn't work. There is a limitation, benefits, everything I can explain. This is why it's called interpretable. So I'll not go much more in that one. So we build a model here, conventional ELM, and slowly we try to reach this model. This is already proposed model. Okay. So IRF ELM. We started from simple ELM and we ended with IRF ELM. You see the performance. This is to remote sensing data. And it is applied on that one. Let me come. The accuracy level. If I go to the accuracy, this is model 1 or model 5. You just now saw that model 1 to model 1 is simple ELM and model 5 is the proposed ELM. See the performance. Okay. More than that, see this particular things. TC, training time. Sorry, not training time. Computation time. You know what is the meaning of computation time? How much time I'm taking to learn and how much time I'm taking to evaluate something. So computation time is total training time plus total testing time. This is the total computation time. See, it is taking 2.35 seconds. Here is 0.54 seconds. Are you getting my point? Why it is happening? Because it's a one-pass learning, right? So time taking is less, obviously. Not only it is taking advantage of this time, also it is giving the better results. So both way I'm trying to get the advantage. Less training time, less testing time, and more accuracy. Okay, that is the advantage of these things. So in different scenarios we have tested. Okay, anyway. So this is what is all about in my application, all the things. And I'll stop here. So I believe I could convey that message, whatever I wanted to convey. And if there any confusion or any doubt is there